All revved up and rejuvenated, raring to go. Well, as I believe I told you during our last gathering before spring break, I took a few days to go with my wife to visit a good friend of mine in the San Francisco area and discovered wall-to-wall people, wall-to-wall cars, wall-to-wall cities, and a place that under no circumstances I would ever live. I don't like that at all. But we did have fun. But I was very happy to come back. In any case, that's just a comment regarding my personal life preferences. Now then, as you know, we have exam 2 booked for this Thursday. But I am trying to figure out a way so you can be provided more time to deal with these activities. So first I'll ask if I can arrange such. Would it be possible for you to do the exam on Thursday, but to begin an hour earlier? Well, let me ask it. Who can't do this? 3 people who couldn't do this. 4 people. Well, maybe in some fashion I could accommodate you 4 in a different fashion, since it's only 4 of you. And in so doing, be able to provide everybody at least 3 hours rather than 2. So I'll ask that you 4 give me an indication, brief note telling me why you can't do this. Well, never mind the why part. But would it be possible for you to carry on for an hour later? I don't like this, but I'm doing the best I can to provide extra time. Now, with that having been said, and I'm sure having raised a degree of confusion, you 4 folks who are involved, if you don't mind, see me for a moment after our chat, or at least sometime early on this week in my office. I've also mentioned the possibility of doing exams Saturday or Sunday. When I asked this before, we had objections, and I'm not at all of a mind to argue with objections. But I'll ask again. If I can arrange such, who could not do the exam on Saturday? All right. If I could arrange such, who could not do the exam on Sunday? Well, we got more problems with Saturday and Sunday than we have with the Thursday business. I'll ask one more possibility. 3 hours for the exam starting at 7:20 on Friday night. Who can't do this? Can't. All right, we'll stick with the Thursday possibility and take it from there. I'll do what I can. And after I have a chance to talk to you folks, the 4 of you who indicated the impossibility of starting at the earlier time of 7:20, well, let's ask the one remaining possibility. Although it's late, at least it provides the extra time. How many would have no conflict in working until 11 p.m. on Thursday?
No conflicts?
No conflicts. Well, no, wait. Conflicts. You get the conflict. Conflict? Okay. We got conflicts no matter how we play the game. All right, I'll do what I can. And to accommodate this, I'll have to see what I get from the 4 of you folks who indicated the conflict with starting at the earlier time of 7:20, and then pursue room. I've already gone after a room, but we'll let you know by Wednesday at the latest. Now then, Last time, in beginning to discuss the material that's at the tail end of chapter 19, which involves another method of getting a salt of limited water solubility to be dissolvable, providing the metal ion component of the salt to react with a material and form what's called a complex ion. We demonstrated this by mixing silver ion with chloride ion to make silver chloride, a material you know to be of quite low solubility in water. But discovered that on treating this with 6 molar ammonia, the silver chloride dissolved readily. At this point I asked the question, which appears to make stronger bonds with silver ion? Is it ammonia or is it chloride ion? The vast majority of you voted for ammonia. Not surprising, since we dissolved readily the silver chloride. And certainly that makes it possible that ammonia makes stronger bonds to silver ion than does chloride ion. But as we'll prove in a moment, chloride ion really makes the stronger bonds. And the reason we got the silver chloride to dissolve readily is silver ammonia complex ion is quite stable. There's no question about that. But what we did was to take advantage of the gang-up factor. We created a system in which the mole quantity of ammonia was far greater than the mole quantity of chloride ion, which is why we got the silver chloride to dissolve. But we did one more investigation on this system. We treated it with nitric acid solution. Before we made the treatment, we asked you to predict what would happen. You all succeeded in predicting the regeneration of silver chloride, as to be expected, because hydronium ion in the nitric acid solution would knock the hell out of ammonia, as well as the silver ammonia complex ion. Indeed, on treating then with the nitric acid solution, back came the silver chloride as we had expected. But I told you also to pay attention to that system as we treated it with the nitric acid solution. That portion of the system which was above the liquid part inside our stoppered cylinder after I added the nitric acid solution, where we saw the development of smoke. And I asked you all to think about, what is the smoke? And I told you it was your job to figure that out time you got here. Well, you're here. What's the smoke? Who knows? Minus 2,000. You get 3 minutes for the exam. How's that? Now let me give you a hint. You did an investigation which parallels this in the laboratory, specifically assignment 2. You remember the work you did with ammonium ion in assignment 2? You recognize that ammonium ion, rather than being precipitated as the cobalty nitrite salt, is much more easily tested for by taking advantage of its weak Bronsted acidity, and on treating with hydroxide ion or a suitable base, but hydroxide ion is the most obvious, converts ammonium ion to ammonia. So if you've got a water solution which you suspect to contain ammonium ion, and you treat it with an abundance of hydroxide ion, you'll convert the ammonium ion in the solution to ammonia, and some of the ammonia will leave the solution as this pungent gas. A pungent gas which is basic. So if you wave damp red litmus paper in this vapor, the red litmus paper turns blue. That you did in assignment 2. But you also found out in assignment 2 that the only test you have for K+ beside flame analysis is precipitation as potassium cobalty nitrite. And that test is interfered with if ammonium ion is present, because ammonium ion also reacts with cobalty nitrite. Upshot: how can I get rid of ammonium ion if I have a solution which I need to test for K+? Heat it up. Heat it up. Here's a picture. put K plus question mark, because we don't know if K plus is in there, but we need to find out. Because we're analyzing an unknown. We found out it tests positive for sodium ion because of flame analysis, so we can't test for K plus by flame analysis. And we've also found out if we take a little bit of this solution and treat it with hydroxide ion, out comes the ammonia. So we know it's got ammonium ion in it. So here you are. What do you do to get rid of the ammonium ion from this system? Tell me. You did this, now what did you do? I want the explicit, specific, correct details. Heat it up. I heard this again. We're going to heat it up. Tell me more. Tell me more about this heat it up. Because if I'm your lab TA and you write down heat it up, I would say, get out of here. Unacceptable.
You leave it over the flame until all the smoke is discharged.
Until what?
All the smoke is gone.
What smoke? If I heat this solution, I'm going to get no smoke. I want to know what's going to happen. I want to know what to do. I apologize for my TAs. I try hard to get them to realize the necessity to have you folks be explicit and detailed in what you do in describing procedures. Because if you put down the incorrect procedure and you're the boss and the person who works for you follows your procedure and screws up the investigation, guess who gets fired? You! Because your directions were no good. How about that? See, I too got feisty over this break time. Ha ha ha. Hell, I was feisty before that. I'll be feisty forever. What do we do? Here's your solution. I want a procedure.
Would you treat it with the cobalt nitrate and the acetic acid and then heat the...
Oh my God, you're going to have a mess.
And then...
You're going to put cobalt nitrate in here and acetic acid? You're going to get K plus precipitated, ammonium ion precipitated. You're stuck now.
And then couldn't you heat the precipitate that forms in the...
Did you do that in lab? Did you heat this precipitate? Then you don't know what happens if you do that, do you? So you cannot possibly suggest that as a procedure to be followed. Right? Because you didn't do that. You got to base this answer on what you have done. All right? Now let's be some more specific. Yes, we will heat this solution. And on heating this solution, what shall we do? What will take place on heating the solution? No. If I heat this solution, the most volatile component of the solution will leave. What is that component? Water. Water! You're going to evaporate the solvent. All right? There you are. $64,000 Van Gogh replication of a Bunsen burner. I'll sell you this for 20 bucks, cheap, and I'll autograph it. Evap solvent. Now I would suggest transferring some of the solution to the crucible and doing evaporation in the crucible. So let's change this to this. Did you notice your crucibles on the side? You'll see printed COORS. Makers of lousy beer. Same company. They make lousy crucibles and lousy beer. At least I think the beer's lousy. Doesn't have much flavor. Doesn't have much pizzazz. I'll take a Heineken any day over that stuff. But that's my taste again speaking. Okay? Crucibles are very thin-walled. They're easily broken. They used to make thicker-wall crucibles, much better quality. Save money. Make junk. Charge more. That's the American way. That's the American way I want you to fight against. There's sermon number 1. After summer break. Spring break. We're going to evaporate the solvent. And now in our crucible, we'll have a solid residue. That's a solid residue. Now what do we do? I move my burner over. Now I'm going to heat the solid residue. What am I observing? The dissipation of what? What will be produced on heating the solid residue? Because we know the solid residue's got ammonium ion in it. Will I see a smoke? How about that? How long do you heat? And I don't want a time response. I don't want minutes or hours or seconds or days or weeks or months. How long do we heat? Until we see no more smoke leaving the crucible. Okay? And now if a residue remains, it may well be a potassium salt. And since we know the sample had sodium ion in it, it's guaranteed a residue will remain. Because you've got to have a sodium salt in there. So you'll dissolve this little bit of residue, which is guaranteed to be water soluble for a 2AB sample, and then follow the cobalt nitrate precipitation procedure for K+. But we're talking about ammonium ion. What is this smoke? Now, let's ask the question in context of what you did in the laboratory. Because what you did in the laboratory was to make a mix potassium chloride and ammonium chloride. Remember doing that? And you were told to take this mix, put it in the crucible, heat it until no more smoke was observed. And now look back in the crucible, the residue remained. That was the potassium chloride. Okay? But you saw this smoke on heating this mixture. What is the smoke? What is it? Ammonia? Ammonia is a colorless gas. What is the smoke? What is a smoke? You did this in 2045. What's the definition of a smoke? Don't tell me cigarette. What is a smoke? You've seen smoke? Absolutely not. It's not a smoke. What's a smoke? You did this in 2045, didn't you? It's a finely divided distribution of particles. What phase? Solid. Yes. Bunch of little solid particulates, finely divided. Since they're so small, they kind of appear to be floating around in the air atmosphere, which contains this distribution of solid particles. So this smoke is a solid. What is this solid? What happened when you heated this in the crucible? You did this. You forced proton transfer from this weak acid to this very weak base. The strong heating did that. So these, which are each colorless gases, left the crucible. But the further they get from the heat, the cooler they get. The cooler they get, the lower their kinetic energy. The lower the kinetic energy, the slower they move. Eventually they collide, and on colliding re-react. And when they re-react, what do these materials make? That is your smoke. You did this. I'm going to have to talk to these lab TAs. Damn it, you're supposed to know this. Fundamental acid-base chemistry. What's this smoke? Inventory the system and you will recognize what the smoke is. We dissolve the silver chloride by treatment with excess 6 molar ammonia. Colorless liquid. System is stoppered. What's up here in this vapor? Beside air? Ammonia vapor, don't you think? And now through this ammonia vapor, we're going to pass hydronium ions and nitrate ions. What are these hydronium ions going to do as soon as they touch those ammonia molecules in that vapor? They're going to convert them to ammonium ion, aren't they? What is the ammonium ions in that vapor going to do when they touch this stuff? Are these anions? Will these anions tend to stick to the ammonium ions? And give you ammonium nitrate, which is the smoke. How about that? If you pay attention to the nature of the system, always keep in mind inventory. You can deal with this. And it's the only way to deal with this. Yes?
Will there be ammonium chloride from the emission also?
No, the chloride's all going to be in solution. There's no reason for the chloride ion to be converted to vapor phase in this system. Okay? So on we go. All that to find out about the nature of a smoke. Well, it's good. Now, fundamental terms and definitions for this part of chapter 19. Complex ion. We already know about complex ions. The name speaks for itself. Rather than a simple monatomic ion like Na plus or F minus for the fluoride ion or Cl minus for the chloride ion, two or more entities, whatever they may have been, have gotten together, reacted with each other, and made an ion which is complex in character. Like this, which is a conglomeration of aluminum ion bonded with 6 water molecules, or a silver ion bonded with 2 ammonia molecules. Ions, of course, because they have charge. Coordinate covalent bond. In 2045, you talked about forming covalent bonds. But I bet in 2045, the covalent bond formation mechanism, which you discussed in the main, if not exclusively, was that of forming a covalent bond by a species with an unpaired electron in its valence structure getting together with another species that also has an unpaired electron in its valence structure. Simplest possible case, H atom, H atom. They get together and these unpaired electrons partner up and become a shared bonding electron pair. So you learn to examine valence electron configurations for the atoms in the periodic table. And if the atom in question has unpaired electrons, you expect it to readily form covalent bond interactions when it gets together with other atoms that have unpaired electrons in their valence electron configuration. Or in the case of species which have no unpaired electrons in the valence configuration, you consider the possibility of promotion. Remember that? To unpair the electrons, like a beryllium atom, which is 2s2 ground state. But heated beryllium is expected to be 2s1, 2p1. Now it's got 2 unpaired electrons ready to make 2 covalent bonds, which relates to the formation of molecular species like BeH2. You did this 2045. But a coordinate covalent bond is a covalent bond formed when an electron pair again becomes shared between the bonding partners, but in forming a coordinate covalent bond, one species by itself supplies the electron pair that's used to make the bond. That's called a Lewis base. And the other species supplies an empty valence orbital. Simplest possible case, H plus interacts with one of the non-bonding pairs on the oxygen atom of a water molecule and makes our good old hydronium ion. So this arrow is intended to show that one of these electron pairs, this one doesn't make any difference, they're identical, will add to this empty valence orbital of H plus. How do you know H plus has an empty valence orbital? Well, it ain't got any electrons. It's derived from the hydrogen atom, isn't it? What is the orbital composition of a hydrogen atom?
1s.
Orbital composition. What is it?
1s.
1s. Hey, hydrogen 1s1, helium 1s2. That's it. That's period 1. All done. 2-electron total electron capacity. You remember how to get electron capacity for an energy level? Period number corresponds to energy level. Period 1, n is equal to 1. Where n is small n, principal quantum number, energy level number 1. Lithium on down through neon. Those are the atoms of period 2. Valence electrons are in energy level number 2. What's the total electron capacity for an atom? Valence electron capacity. Total valence electron capacity for an atom in period number 2. 8. How do you get that? You remember the recipe 2n squared. N is the period number. N is 2. Well then, n squared is 4. And 2 times 4 is 8. Now then, back to our definitions. Electron pair acceptor. Lewis acid has one or more of these kind of valence orbitals. I told you before what this means. Empty. 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 Okay. So, as necessary, you need to pay attention to valence electron configurations in order to determine if a species can be a Lewis acid. Lewis base. Electron pair donor. Now be careful about this word donor, because the Lewis base supplies the electron pair to become a bonding electron pair. It's not that the Lewis base gives away the electron pair. It doesn't lose the electron pair. It just takes an electron pair which it possesses all by itself and uses this electron pair to become a shared bonding electron pair, to make the link between the Lewis acid and the Lewis base, as in forming here the hydronium ion. Now, how do we recognize the valence quality of a Lewis base or potential Lewis base? Well, it's got one or more valence non-bonding pairs. Also, on occasion, a pi bonding pair can be used to make a coordinate covalent bond. But we'll not concern ourselves with pi bonding electron pairs that are used to make coordinate covalent bonds. Not at this time. We got enough going on with this consideration. So tell me, what would you do if given a formula for a species, if asked the question, can this species be a Lewis base? What will you do to find out if this species can in fact be expected to be a Lewis base? Yes! You're right, it's Lewis structures. Have we got any non-bonding pairs? And most species do. So most species can be Lewis bases. Lewis acid, Lewis base reaction. We showed one over there. There's another one. Aluminum ion gets together with 6 water molecules to make this thing. Here's a picture of its structure. Water molecule. These beautiful red things simulate the non-bonding electron pairs on the oxygen atom, simulated by this black part of this model. Ooh, these nice silvery hydrogen atoms. After 6 of these, use one of these non-bonding pairs from each of the 6 to make a coordinate covalent bond with the aluminum ion. Ding! You just made a bond. My noggin is the aluminum ion, and now I have been coordinated by this water molecule. And when this happens 6 times, I get this kind of structure. What's this shape? You'll learn this in 2045. What's it called? What is it? An octahedron. Because if I draw this as a solid geometrical figure, I'll see that it has 8 perfectly triangular faces. Octa 8. Hedral face. 8 faces. Octahedron. Okay? That's what it looks like. And we'll talk when we get to chapter 22 about how this, in this case which simulates our hydrated aluminum ion, can behave as a Bronsted acid. It's in chapter 22. One more on that later. What I want to ask now is, and students often ask this question, and it's a good question. When the aluminum ion reacts with water molecules, why do I stop at 6? 6 water molecules. Why do I go as high as 6? Aluminum ion is derived from aluminum, which is an atomic member period number 3. How many valence electrons can be contained in the valence environment of a period 3 atom? How many valence electrons, max number of valence electrons, containable in the valence environment of a period 3 atom or ion? 18, that's right. So how many valence orbitals? 9, because you can put 2 electrons in an orbital max. What are these valence orbitals for a period 3 atom? 3s, 3p, and a p sublevel is a package of how many orbitals total? 3, and then comes d. And a d sublevel is a package of how many orbitals? 5. So 3s, 3p, 3d. Total orbital capacity of these 3 sublevels added together gives you 9. Well, why don't I get aluminum complexed by water with 9 water molecules? This has to do with BBs and basketballs. You know about BBs and basketballs? How many BBs can I glue to a basketball? How about a hell of a lot? How many basketballs can I glue to a BB? How many? 2. That's it. So, what it amounts to is, even though I can theoretically make 9 coordinate covalent bonds with this aluminum ion, because it's got 9 empty valence orbitals, we just talked about that. It stops at 6. Because there isn't enough space around an aluminum ion. It's too small. I can't get more than 6 water molecules close enough so that each of the 6 water molecules through the oxygen atom end can make contact with the aluminum ion and make coordinate covalent bonds. Yeah, this parallels activities in which college students regularly engage. Like how many students can I get in a VW Beetle? They do stuff like this. I think the answer is less than 400. This is small students at a small college. Now then. Back to this. H plus is our Lewis acid. With which of these Lewis bases will H plus interact most strongly? Now before you answer that, let me tell you that each and every Bronsted-Lowry acid-base reaction is also a Lewis acid-base reaction. Each and every Bronsted-Lowry acid-base reaction is also a Lewis acid-base reaction. Because each and every Bronsted-Lowry acid-base reaction involves H plus transfer. So H plus is always behaving as a Lewis acid in every Bronsted-Lowry acid-base reaction. With which of these 3 Lewis bases does H plus interact most strongly? You know this. Which one? Which one? Ammonia. Four non-bonding pairs. Only 1. So immediately recognize that Lewis base strength got nothing to do with the number of non-bonding pairs in the valence environment. Explanation? You put this one in there too. This kind of stuff we're going to do extensively in chapter 22. The explanation lies here. What is that? Electronegativity, you betcha. Now, before we talk further about this, let's put silver ion in the game. Same 3 Lewis bases. Which of these 3 Lewis bases does silver ion interact with preferentially? Well, I already told you the answer, didn't I? It's chloride ion. Yet, this is a monatomic cation, charge +1. Monatomic cation, charge +1. Yet this +1 cation sticks much more strongly to ammonia, whereas this +1 cation sticks much more strongly to chloride ion. And in water solution, chloride ion doesn't even get in the game for this. So this is telling us, if you want to assess the progress of a Lewis acid-Lewis base reaction, you have to pay attention to the Lewis acid as well as the Lewis base. So that shows us this is a lot different than Bronsted-Lowry acid-base chemistry, where we can assess in an absolute fashion the Bronsted strength of an acid or base. You can't do that with Lewis acids and Lewis bases. Silver ion, chloride ion. What can silver ion do with chloride ion that silver ion can't do with water or can't do with ammonia? Now, I don't suspect that you would grasp at this right away, but you have the knowledge, or should have the knowledge, which allows you to wrestle with this. The answer is silver ion can make much stronger bond interactions with chloride ion than with either water or ammonia, because with chloride ion, silver ion can engage in multiple bond formation. Pi bonds. Pi bonds. How could chloride ion make pi bonds? Whereas ammonia molecule can't, neither can water molecule. Chloride ion can make pi bonds because it's got empty valence d orbitals. And silver ion has an abundance of valence 4d electron density. Upshot, you can make pi bonds. But more on that now. That part, for now, that's just to put some information in your noggin, and we'll refine it later. Back to this, the thermodynamic aspects of this reaction. Here's the reaction that we studied and ran. Here is calculation of K. And when we get this K value, we're already seeing that it's the case. Since K for this is 0.0029, the silver chloride is a more stable stuff than the silver ammonia complex ion. But given the K value is much smaller than 1. So try this. Mix 1.0 moles silver chloride with 1.0 liters of 6.0 molar ammonia. Calc EQ composition. All we need is this reaction. So that you will know what I'm doing specifically from an algebra standpoint, I'll write down, let's allow S to represent the solubility of silver chloride in 6.0 molar ammonia, given that we've used S throughout Chapter 19 to refer to solubilities. Why S for solubility? Because this treatment is going to get some of the silver chloride to dissolve and become the silver ammonia complex ion. Okay? So with this we get 0.0029 is equal to this K expression. Well, if S is the solubility of silver chloride, 6.0 molar ammonia, then S will compare how to the silver ammonia complex ion concentration? Equal to. What will the chloride ion concentration be in terms of S? Equal to. What will be the equilibrium molarity of ammonia in terms of S? What was the molarity of ammonia with which we began? 6.0. In terms of S, how much ammonia got consumed to establish this equilibrium? How much? How much? How much? 2S, right? You got 2 multiplier. We've done this before many times. So what do I have? S squared over 6.0 minus 2S quantity squared. So how do I solve this in the most expeditious fashion? I do this. You agree with that? Perfect square. So I get S over 6.0 minus 2S equals the square root of this 0.0029. Will the square root of 0.0029 be bigger or smaller than 0.0029? Bigger. But you know how to do the arithmetic. And when I do the arithmetic, I get S equals 0.29 equals this. Thus, if the equilibrium molarity by this mixture, if the equilibrium molarity of the silver ammonia complex ion becomes 0.29, then it follows that 0.71 moles of silver chloride is still there undissolved. And look at the mixture that I made in terms of its composition, in terms of its inventory. In this mixture, I got 1 mole total of chloride ion, 1.0 moles. And I got 6.0 moles total of ammonia. So the ammonia is outnumbering the chloride ion 6 to 1. Yet stoichiometrically, I need to outnumber the chloride ion 2 to 1 for this to go. If this was a 100% efficient reaction, if I make a mixture in which there's at least 2 moles of ammonia per each mole of silver chloride, I'm going to dissolve all the silver chloride. If the K value for this thing was big. Ha-ha! But we saw that K value isn't big, is it? And we just found out with this analysis. Outnumbering silver ion and chloride ion 6 to 1 with ammonia still leaves the vast majority of silver ion in contact with chloride ion. So who wins the stronger bond game with chloride ion? I mean with silver ion. It's chloride ion easily. And again the answer is a consequence of the much stronger bonds that silver ion makes with chloride ion because of the ability of silver ion and chloride ion to get together with each other and make pi bonds, which silver ion can't do with ammonia or with water. Now, tomorrow, you're going to jump into chapter 20. I remind you right now that the majority of chapter 20 is stuff you've already done in Chemistry 2045. So we're not going to spend much time on chapter 20 stuff. So you can well expect chapter 20 stuff to be on this second exam. And on Wednesday, I'll finish up chapter 19 and jump into chapter 21 in order to get us ready for all the stuff that you can expect to be responsible for on exam 2 with this stipulation. In chapter 21, you will see that the first topic discussed in chapter 21 is the phase diagram for water. You all looked at the phase diagram for water in Chemistry 2045. How many of you understood it? How many of you were asked to realize in Chemistry 2045 that when the damn stupid textbook discusses the phase diagram, they can't really do it because a phase diagram is a free energy diagram. And the stupid textbook doesn't talk about free energy until way past that chapter when it discusses phase diagrams. And you wonder why I get mad at these textbooks. They're asking of you that which is impossible. Yet they keep on doing the same damn thing over and over again. Terrible. We're not going to make that mistake. Go ahead.